I hope you guys had a great weekend. Are there any questions? All right, so my policy is the due date for sapling is 2 days after we finish it in lecture. So that means that I'm going to move the due date for chapter 22 Wednesday. All right? So somebody has to remind me though. I'm worried I'm going to forget because I'm a judge at the Mr. Medicine competition today, so I might forget. So somebody has to send me an email to remind me. Just you, not everybody, please. Anyway, questions? Yes? Wednesday morning at what time? Oh, that one. Yeah. I need to follow up on that, yes. Okay. Send me an email to remind me. My mind's on Mr. Medicine right now, so I'm going to forget. Okay. All right. So we left off last time talking about synthesis. And we had two different routes. And we decided that if we were going to use CO2, that it would be better not to use the lithium route. Better to use Grignard. So let's branch off here. Oh, what do you mean? Oh. How about that? We decided that it would be better not to use the lithium route for CO2 because it will add twice. So we want it just to add once, so we're going to do Grignard instead if we're going to do the other pathway. So we're at a point now where there is going to be more than one pathway. And so that makes grading trickier on exams. So you really want to make sure when you get your exam back, some people, if they don't do well, they won't look at their exam. And you might have things marked wrong that were correct. If you have a unique pathway that I didn't anticipate, you might have got it marked wrong. So you definitely got to make sure that you check it out. I want you to get the points that you deserve. All right, so then we do CO2. Followed by H3O plus. This is a little bit longer pathway, but we don't care as long as it gives us what we want. Oh, we protonated, so I got to protonate that. And then what do I do? We got to reduce that carboxylic acid to an alcohol. So we could use lithium aluminum hydride, step 1. Followed by H2O to give us the product. So that's one step longer, doesn't matter, as long as you get the right product. Questions about that synthesis, anybody? Yes?
If we made a Grignard and then use formaldehyde, would it still work?
Absolutely, yeah. So you could do the same thing here. So this could be, rather than organolithium, that could also be a Grignard. No problem with that. All right, so let's look at the third example. This is devise the synthesis of the following compound from compounds having 4 or fewer carbons. All right, so this one's a little bit more complicated. More complicated carbon skeletons here. So what's popping out at me immediately is that carboxylic acid, the CO2H group. And I'm going to go retrosynthetically here. And I know I can make it the same strategy we just did here. So make a Grignard, and then we have CO2. And then we follow that by adding acid to make a carboxylic acid. Okay, and the Grignard I can make from corresponding alkyl halide. And then I can make that halide from the corresponding alcohol. So we all of a sudden in this chapter have gotten much more sophisticated in the things that we can synthesize. When we were building carbon skeletons before, it was all using deprotonated acetylene, and that was a little easier to see. This is a little harder to see. All right, so but we know we have a bunch of ways of making alcohols in this chapter. Certainly Grignard's a good way of making alcohols. We have to have 4 or fewer carbons. So what I'm thinking is that we have, let's see, 1, 2, 3, 4. I'm thinking if we break right here, and then this is 1, 2, 3, 4. Those are 2 4-carbon pieces. So how am I going to make this bond right here? I'm going to make this bond by making a Grignard and attacking an aldehyde. So, and again, there's more than one way to do this, but that is certainly a method that will work. So I'm going to make this using an aldehyde. So the alcohol side would be the aldehyde, and then this side would just be a Grignard. Or a lithium. Let's just make it lithium here. Okay, so that's what that would look like. Each carbon is 4 pieces, and the lithium reagent I can certainly make from the corresponding alkyl halide. And I'll just use bromine here. All right, everybody following that retrosynthesis? Let's write out the synthesis in the forward direction. So that's sort of the thought process that we have before we write out the synthesis in the forward direction. On the exam, we don't grade thought process because it's too difficult to grade. So you definitely want to write out the synthesis in the forward direction. All right, we could have made a Grignard also. They're interchangeable for this reaction. So there's our 4-carbon aldehyde. We follow that with water. That gives us the alcohol we're looking for. And then what do we want to do there to turn that into? We want to turn that into a bromide. What would we use? PBr3 pyridine. Would not want to use HBr here because things are going to rearrange. That's not what we want. PBr3 pyridine. We'll turn that into a halide. And we could make a Grignard or organolithium reagent. Well, we definitely want to make a Grignard here. Mg ether, because we're going to be using CO2. That makes the Grignard. So this would be a reaction where I would call it open-ended, and you have to write the products from each step. But protonation steps you can include with the previous reagent. So then we would have this, CO2. Not too many of these types. They're very difficult to grade. I usually have things in a box with an arrow, and then you fill in each step, okay? Questions, anybody on that synthesis? So pretty sophisticated. This is definitely what we want to do is we want to practice doing synthesis. Yes, question?
Do we have to start with the bromide or can we start with the organolithium?
You could start with the organolithium. Just whatever the directions say. If it says only organic compounds, then you would want to make the organolithium compound. Okay? Just depends. All right, any other questions? Yes?
Thank you. Would we be able to use H3O plus rather than H2O in the final step?
Yes, certainly, and it should be H3O plus, right? Actually. I'm not going to make a big deal about this.
Thank you.
Yeah, it should be H3O plus. We already showed that water's not strong enough, right? That's more correct. Okay, more questions? Yes? Okay? Yes? You can use magnesium. You don't have to use a lithium reagent there. You can make, students tend to like Grignards better, right? You guys like Grignards better. People use Grignards more often than anything else. And that's perfectly fine. Okay, so that is the end of chapter 20. We're going to start chapter 21. All right, so this is all about, in this chapter we're going to talk about reversible reactions of type 1 carbonyls. In the next chapter we're going to talk about reversible reactions of type 2 carbonyls. Okay, and then we're going to get to the more complicated carbonyl chemistry. All right, so just to give you some ideas of why ketones and aldehydes type 1 are important, we have, anybody recognize this compound here? Testosterone. We got a bit of that in this room, don't we? And progesterone here. So we have some steroids here. This is glucose open chain. We'll talk about open chain and glucose. That's coming up in our very last chapter this quarter, your last chapter of OChem. So that's the open chain form of glucose. So you see the aldehyde. And aldehydes and ketones figure prominently in perfume manufacturers. They use, a lot of them smell really good. This smells like pistachio. This one smells like camphor. We have maraschino cherries for the aldehyde. We have cinnamaldehyde, which smells like cinnamon. We've got raspberry flavoring. We've got vanillin, which smells amazing. We're going to use that in this quarter in my lab, and the whole lab smells like vanilla. It's nice. Oil of violets. And then we have this compound here where the different enantiomers sell differently. We have spearmint for one of the enantiomers and caraway for the other enantiomers. So the receptors in our nose are chiral. So these are going to smell differently. Nomenclature of aldehydes and ketones. We're going to wait till next chapter to do our nomenclature. Okay, so right now we're going to shelve that. Preparation of aldehydes and ketones, those are the sections you want to review. Chapter 21, 6A and B. We just had that, right? So we don't need to do that now. Physical properties of aldehydes and ketones. We'll jump right ahead here. So here's some compounds with similar molecular weight. Minus 6.9. Do not need to memorize these numbers. We're just talking about trends here. Aldehyde. Similar molecular weight aldehyde. 20 degrees centigrade. 56 for the ketone. That makes sense because it's got one more carbon. So as we increase molecular weight, we increase boiling point. And then here, similar molecular weight, but this one is 82.3 degrees centigrade. Why is that one so much higher boiling point? Hydrogen bonding, yeah. Okay, so this one here, these are hydrogen bond acceptors only. So that means that these guys, when you put them in water, they can hydrogen bond with water. But when they're by themselves, which they are when you're doing boiling point, there's no hydrogen bonding that can take place. So hydrogen acceptors only can't hydrogen bond with itself or other molecules of itself. Whereas this one right here, hydrogen bond donor plus acceptor. And so that one has the highest boiling point because it can hydrogen bond with itself. All right, so that makes good sense. Percent solubility in water, 0% for the alkene. Infinite for all of these guys. Dipole moment, 0.5 for the alkene, 2.7. I've seen different numbers for these. The aldehyde and the ketone, similar, but they're not exactly the same. I think this number's from your book. I'm not sure. 2.7, so similar dipole. And then 1.7 for the alcohol. So even though we have a smaller dipole, the alcohol has a higher boiling point because of hydrogen bonding. And solubility diminishes rapidly with added carbon. So if we just take and we add one more carbon onto acetaldehyde here, we go from infinite solubility to 20% solubility in water. All right, so that's all we're going to say about physical properties. Reversible Addition reactions of aldehydes and ketones, that's the main subject of this chapter. As we saw in chapter 20, we have strong nucleophiles, organolithium, Grignard, hydride, and sodium alkanides. Once they add to the carbonyl, they're on for good. They cannot come back off again. So those are irreversible additions. With weaker nucleophiles, so we have water, alcohols, primary and secondary amines, and cyanide ion, the reaction is reversible. So we're going to get different products here because of this. We're going to go in this order. We're going to start with water, and then we're going to talk about alcohols, and then amines, and then cyanide last for all of the reagents that do reversible addition. We will start with water for hydration. This is what the reaction looks like. We'll just use acetaldehyde here. Acetaldehyde in the presence of water with a trace of acid or base. Only trace is all you need. And if you do that, you get, this is a new functional group for you. This is called a hydrate. It's also called a geminal diol. So geminal means that the two alcohols are on the same carbon, but more commonly, the hydrate is more common. So that's a new functional group that you need to know. So it's a carbon that's attached to two hydroxyls. Yes? No, actually. The arrow should not be the opposite direction. So we actually favor the aldehyde. Aldehyde's more stable. So this is thermodynamic conditions. And under thermodynamic conditions, it's you favor the more stable species. This is more stable. So you only get like a little bit of this forming. It's a very small amount. Okay, so even, if you think about it, even, that jar of acetone that you have to clean things in the lab, that's got a little bit of hydrate in there. You didn't realize, but it does. Okay, so you have to work really hard to get rid of excess acid or base. You only need a trace. So this is a reaction that happens to a very small extent to the right. If you want to actually isolate hydrate, you have to drive the equilibrium. Otherwise, you won't be able to isolate very much. All right, this is going to have this has an acid and a base catalyzed mechanism. So it's going to remind you of a reaction from chapter 9 where we had an acid and a base catalyzed mechanism. You remember that? Opening up epoxides. Remember that? I made a big deal about that mechanism. I put it on the exam, and the reason I made a big deal about it is it kind of prepares you well for carbonyl chemistry. So a lot of these reactions have an acid catalyzed and a base catalyzed mechanism. And you need to know both, and you want to avoid the common pitfalls. The same pitfalls that you have when you did the epoxide ring opening. So when you have an acid catalyzed mechanism, you protonate things with H3O+. You don't protonate things with water, because if you protonate things with water, you get hydroxide ion. In a base catalyzed mechanism, you protonate things with water to produce hydroxide. So you want to kind of keep your species separate. In the acid catalyzed mechanism, we don't want to be making negatively charged species. And in a base catalyzed mechanism, we don't want to make hydronium ion, because it's not going to be present in an acid catalyzed mechanism. So we'll do base first. And so that is a trace of hydroxide, so you only need a catalytic amount. And if you could remember what happened with hydroxide and an epoxide, it just directly attacked the epoxide, right? We did not protonate first. And it's going to be the same thing here. So hydroxide ion is going to attack, hydroxide ion, great nucleophile. So it's going to attack hydroxide, it's going to attack the carbonyl directly. So great nucleophile. It attacks carbonyl directly. All right, so the arrow is going to come from one of the lone pairs on oxygen. We're going to attack the carbonyl carbon, kick electrons up onto oxygen. reversible arrows here, because that can come right back off again. And a lot of the time it does come right back off again. If we want to actually isolate hydrate, we have to drive the equilibrium. So it looks like that, and then we protonate here. Base catalyzed mechanism, we protonate with water, and when we do that, that's good because now when we do that, we're regenerating our hydroxide catalyst, right? So to check that you haven't made a mistake, see that you make sure that you regenerate that hydroxide in this last step here. We have that, and then we regenerate our hydroxide again. And that can now go and attack another carbonyl. So hydroxide attacks directly, and then we protonate with water. Do you see why we wouldn't want to protonate with H3O plus here? That's a very common mistake on exams, to protonate with H3O plus. Are we going to have H3O plus in a base catalyzed mechanism? No, so that's why you don't want to use that. We want to actually regenerate our hydroxide. So that's the base catalyzed. You need to know the base. You also need to know the acid catalyzed mechanism. So for acid catalyzed, trace of H3O plus present for the acid catalyzed mechanism. So if you can remember back to epoxides, what do we do in the acid catalyzed mechanism? We protonated the oxygen first, right? We're going to do the same thing here. So nice to be able to draw that parallel here. We're not going to protonate with water, because if we protonated with water, we'd make hydroxide ion, and we don't want hydroxide ion appearing in an acid catalyzed mechanism. So we're going to protonate with H3O plus. So arrow comes from the lone pairs on oxygen. We grab a proton and we push electrons onto oxygen. So it looks like that. That's our first step. And that's an important first step because protonation makes the carbonyl more electrophilic. We mentioned that, and now we're seeing it in use here. Protonation makes the carbonyl more electrophilic. We're going to talk about why in class today, in discussion this week. More electrophilic. So weak nucleophile. Water's our weak nucleophile, can attack. So in the base catalyzed mechanism, the nucleophile attacks the carbonyl first. In an acid catalyzed mechanism, we protonate the oxygen first, and then the weak nucleophile attacks in the second step. So in the base catalyzed, we protonate in the second step. In the acid, we protonate in the first step. So here's our weak nucleophile. We know that water is a very weak nucleophile. And so what we need to do is soup up the electrophilicity of that carbonyl so that our weak nucleophile can attack. So it looks like that. So we have reversible arrows all the way through here. At any point, we can reverse back again. So this keeps going forward, backward, forward, backward. It could go up 2 steps and back 1 step and then forward again, or it could go up 3 steps and back 3 steps, and it's just every single step is reversible. If we want to isolate a single product, we definitely need to drive the equilibrium. All right, so now we have, we've protonated the oxygen first. We have the weak nucleophile attack. What's the last step? We have to have some sort of base come in. And I don't want you to use B. B minus, generic base. Well, what is our actual base here? It's water, not hydroxide. If we use water, then we are regenerating our catalyst. And we don't want to use water to protonate, or we don't want to use hydroxide to deprotonate because this is an acid catalyzed mechanism. We're not going to see hydroxide in here. Need to know the mechanism in the forward and the reverse direction. And forward and reverse direction. So we're doing the forward direction right now, and then in discussion we're doing the reverse direction, actually twice in this worksheet for this week. Questions so far? Anybody? All right. Formation of hydrate is reversible, as we kind of made a big point about with all these reversible arrows. By the way, when I'm grading mechanisms on the test, I only grade curvy arrows. So I only grade this part here. I don't grade whether you have reversible or forward arrows, so you don't have to worry so much about it. But I'm trying to show it here because all of those steps are definitely reversible. Factors that favor addition, which is formation of the hydrate. More stable the carbonyl, the less favorable the addition. That makes sense. The more sterically hindered the carbonyl compound, the less favored the addition. So we're doing an addition here. And so it makes sense that the more reactive the carbonyl, the more hydrate we're going to form. And if we have a really unstable carbonyl, then the hydrate actually can be favored in some instances. So let's compare here. We have acetaldehyde versus ketone. We've talked about this already. We talked about this one. Let's do it again. And we're seeing which one of these is more electrophilic. All right, so we know that methyl is an electron donating group. All right, so that's going to donate a little electron density into that carbonyl, making it a little bit less positive, right? So one electron donating group makes carbon less positive. Over here we've got two of them. So that's double the effect, isn't it? So two electron donating groups make carbon even less positive. Less positive means more stable. So that was our inductive effect. It's a very slight inductive effect with methyl, but it's there nonetheless. And then our second thing was resonance effect, or steric effects. So this one here, aldehyde is less sterically hindered. This one is more sterically hindered. So it's got two methyl groups. More sterically hindered, that means it's going to slow down the rate of the nucleophile attacking the carbonyl. So more sterically hindered. And so what we can say, both of these effects actually work together. This compound, a ketone, is less subject to nucleophilic attack. Another way of saying that is that it's less electrophilic, right? Two ways to say the same thing. So it's more stable. And since it's more stable, the hydrate is less favored. So we can completely correlate the hydrate formation and the extent of hydrate formation with how stable the carbonyl is. Looking at this next example, we both have aldehydes, but as you can see, when we put fluorines here, we have a pretty dramatic effect here. These fluorines are going to pull electron density away. There's 3 of them, so they're already powerful on their own, and now we have 3 of them. So if we're comparing partial positive charge on the carbonyl carbon, which one of these guys is going to be more electrophilic? First one or the second one? Second one, by far. So electron withdrawing fluorines. Make the carbonyl carbon more positive. Therefore, it's going to be less stable. Therefore, it's going to be more electrophilic. All of these are interchangeable ways to say the same thing. More electrophilic, more subject to nucleophilic attack. Whoa. More subject to nucleophilic attack. And if it's more subject to nucleophilic attack, then the water's going to want to attack it and make a hydrate, okay? So that means that the hydrate's going to be more favored. All right, so all different ways to come to the conclusion that the hydrate's going to be more favored. Let's do one more where we're comparing reactivity. So very good possibility that you're going to have something where you're comparing a reactivity of carbonyl compounds. We already talked about that all mixed, and then we could have one where we have aldehydes and ketones with electron withdrawing groups, things like that. All right, so we have, again, we're doing the same thing. We're comparing partial positive charge on the carbonyl carbon, seeing which one has the most partial positive charge. And what you can see here is that we do have resonance stabilization. This is benzaldehyde, and we do have resonance stabilization for benzaldehyde. So we can draw that resonance structure, and we can keep going. Here we can draw a bunch of resonance structures. Let's do one more. This is starting to look like chapter 18, isn't it? All right, so highly resonance stabilized, right? So benzaldehyde, highly resonance stabilized. More stable is less reactive. So therefore, less electrophilic. We could also say less subject to nucleophilic attack. We could say all those things. And then we can also conclude that the hydrate is going to be less favored. All right, so here's a chart here. You do not need to memorize these numbers, but you're definitely seeing some trends here. Now, so remember, this is the equilibrium constant here. So if the equilibrium constant is greater than 1, that means the reaction is favored to the right, which forms the hydrate. So here's hydrate over here. And if the equilibrium constant is greater than 1, then the hydrate's favored. So what do we see? Formaldehyde, hydrate's favored. Acetaldehyde, we have about a 1-to-1 ratio here of this and this. Ketone, 1.4 times 10 to the minus third. So ketone is favored. Are you seeing this all coming together here? 3 fluorines for acetaldehyde. Now it's going to see we go all the way from here. Here's 1.06. With the 3 fluorines, we make this more electrophilic, and so we also get more hydrate. Okay? Phenyl ring here, that's not favored. Okay, we just showed that that was less electrophilic, more stable, so less hydrate. Ketone here, we actually can favor the hydrate when we put the 3 fluorines here. And the more fluorines, the better, right, for making hydrate. And then, so you definitely see the trends here. Okay, so that's what we're talking about. So don't want you to memorize those numbers, but if I had a bunch of aldehydes and ketones there and I asked you, to rank them or to tell me which one's going to form the most hydrate, which one's going to form the least, you'd be able to answer that question just based on understanding that chart. Okay? Questions? Yes? They do, but they're still contributing structures. It's not a major thing. The proof is right here in how much hydrate you form, right? So we go from here, that's 1.06, and now we go here, and it's 8 times 10 to the minus third. That's really the proof, that that is playing a role. Over here was another question? No? Okay. That's hydrate. And we're going to be able to make the same approximations when we're, the same sort of statements when we talk about the addition of alcohols to ketones and aldehydes. All right, and we're going to have a base catalyzed reaction and an acid catalyzed reaction. The only difference here is that the base catalyzed, you get a different product, actually, than you do the acid catalyzed. So this one's a little bit more difficult. So here our nucleophile is alcohol, HOR. So base catalyzed reaction is going to look a lot like hydrate. Move it up just a little bit. Yeah? Better? Oh, because it was off the top. Okay. Reversible arrows. I'm not going to show either. I'm not going to show any particular direction. CH3O minus is our catalyst. Trace a base. That's a new functional group. We have a carbon that's bonded to a hydroxyl and a methoxy group, and that is called a hemiacetal. So we have a bunch of new functional groups in this chapter here. That's a hemiacetal. A carbon that's bonded both to a hydroxyl and a methoxy group or an alkoxy group. The mechanism is going to completely remind you of base catalyzed hydrate formation. All right, so our nucleophile is methoxide ion. That's a good nucleophile, right? We're not going to protonate the carbonyl first. We're going to attack directly. So we're going to, arrow's going to come from one of the lone pairs on oxygen. We're going to kick electrons up onto the carbonyl oxygen. Reversible steps, so I'm having reversible arrows. So when we use the base catalyzed, we attack the carbonyl first with the base, and then we protonate second. And we want to protonate with methanol so that we regenerate our methoxide catalyst. We don't want to protonate with acid. That's a very common mistake to protonate with acid here. And we don't have acid because this is a base catalyzed mechanism. And a lot of students who aren't really very prepared for the exam will use a combination of acids and bases in their mechanisms, and you usually don't get any points when you do that. So you want to keep that straight. There's our hemiacetal. Questions on the base catalyzed mechanism? Yes?
Why doesn't methoxy also act as a leading group like it did last?
It could. That's why the reaction's reversible. Okay, so what happens here, we have this attack, kick electrons up onto oxygen, and the electrons on oxygen come down and can kick off methoxy. That's why we have reversible arrows. It's going to keep going back and forth. If you want to isolate a hemiacetal, you have to drive the equilibrium because this wants to be here. Wants to be as a ketone. Unless it's one of those really activated ones that we talked about on the previous page. All right, acid catalyzed. So what are we going to do first? Protonate the carbonyl first. So for all the acid catalyzed mechanisms that we're going to talk about, we're going to protonate the carbonyl first with acid. And there's only one exception that we're going to have in this chapter, but in everything else, we're going to protonate the carbonyl first. All right, so let me just write out the reaction here first, and then we'll do the mechanism. H3O plus, or just protonated methanol. So you can just add a trace of H2SO4. You'll make protonated methanol here. So that would be our catalyst. We can form a hemiacetal, but typically hemiacetals are difficult to isolate. There are some exceptions, and we'll talk about those coming up. But this is the hemiacetal, generally not isolable. It keeps going, and we're going to form actually a different product here. So hemi for hemiacetal, and then this is an acetal. So hemi half acetal. So this one had this. So there's another new functional group, and we're not done. We have a few more. So this is an acetal. So an acetal is a carbon that's attached to two alkoxy groups. All right. I'm going to show you the mechanism for this. This is a mechanism that 99% of the time I put on midterms. Okay, so very highly likely that you will have this mechanism on midterm 1. I'm not going to say for sure because I want a little bit of freedom here when I'm writing the test, but most of the time I do. All right, so first we're going to form the hemiacetal right here. We have it showing right here. And then, so we're going to do that mechanism. And then the second part, we form this, and then we go from the hemiacetal to the acetal. All right, so this is what it looks like here. So as we said, acid catalyzed mechanism most of the time. 99% of the time. There's one exception in this chapter. But most of the time we protonate the carbonyl first. And this is just like what we did in chapter 9 where we protonated the epoxide first. Same idea. Notice the reversible arrows. All these steps are reversible at any point in this mechanism. We can just go back again. It's an equilibrium process. The product of this reaction is going to be an acetal. It is not favored. It is more stable to have a ketone than to have an acetal. So we have to drive the equilibrium. We'll talk about how you do that. All right, our nucleophile is methanol here, and methanol is a weak nucleophile, and so we protonate the carbonyl to make it more electrophilic so our weak nucleophile can attack. So weak nucleophile attack the carbonyl carbon, we kick electrons up onto oxygen. So far it looks just like hydration. All right, so what do we need to do next? Same thing we did with the epoxides, right? We protonated the epoxide first, the alcohol attacked, and then we deprotonated the alcohol. We're going to do the same thing here. And once we do that, we have the hemiacetal. So there's a hemiacetal. Again, generally can't isolate that. So it's going to keep going. And that's on the next page. All right. So I'm going to redraw the hemiacetal. All right, so what we need to do here to go to an acetal, this hydroxide ion needs to be replaced with a methoxy group. So what's going to happen is that this group is going to leave, but it's not going to leave as hydroxide. Why not? Hydroxide is not a good leaving, number one. And number two, well, I mean, we had it in the hydrate, but we're in an acid-catalyzed mechanism. We don't want to be making hydroxide. So we're going to protonate that first. So depending on what you have here, we can use hydronium ion if we had catalytic hydronium ion. Or we can have the protonated alcohol, which behaves just like hydronium ion, right? Both of these have negative pKa, so they're really strong acids. Okay, so we're going to protonate the hydroxyl. The hydroxyl is what's going to leave. So we're going to, oh, what happened? I'll just use H3O plus here. You can use either one of those species. Now there's two ways to do the step after this. I'm going to show you the way I do it, and I'm going to show you the way the book does it, and you can do it either way. Doesn't matter to me. I like my way better, of course, but you don't have to do it my way. Okay, so the way that I do it is that I have the electrons on this oxygen come down and help kick off that leaving group. So they kind of push that leaving group right off. And you get this species here, which kind of looks like a protonated carbonyl, and it behaves like a protonated carbonyl, except that we have a methyl there instead of a hydrogen. The book shows it, and we're going to keep going here. We're going to run out of time here, but the book shows it this way. So let me show you. The book shows this way. And then we'll keep going. We won't be able to finish this today, but the book shows it this way for that step. So once you have this compound here with the protonated alcohol ready to go, it has that group leave to make a carbocation. And a lot of students like this way better, and that's perfectly fine. And then they have these electrons come down to draw the resonance structure. I went directly to the resonance structure. I will accept both ways. Both ways are okay. Both ways, okay, and then we will. So that's this step right here. That's this step, and we will finish this mechanism next time.